Hello everyone, I'm very honored to participate in this conference. I'm so glad to have the opportunity to introduce our paper SBP-CPI, which can predict compound-protein interactions-based neural networks. Here is the outline. I'll introduce our paper from these four parts. Identify interactions between compound and protein is a substantial part of the drug discovery process. The interaction analysis technique based on the experiment is expensive and time-consuming, so it's very meaningful to study the computing method to identify the relationship between compound and protein. There are two main computation-based methods, molecular docking and machine learning. In the docking method, interactions are evaluated by attaching pair of molecules to protein binding sites and then calculating the energy between the two. However, this method has two disadvantages. While the machine learning method directly uses data information to predict binding affinity or binding interactions, thereby avoiding the study of complex physical functions associated with docking, and improving efficiency. Naive Bayes, KNN, random forest, and SVM are traditional machine learning methods. Some researchers have developed methods based on deep learning, like DRAG-VQA, DeepTTA, and Transformer CPI. Next, I'll introduce our method. It consists of three parts: compound, protein, and classification module. This figure is the overall architecture of the model, which can be divided into three parts: the feature extraction of compound and protein, and the classifier part. CRS model was used to extract features from compound distance matrix, and the Dot-Vector model was used to extract protein sequential features. Finally, the extracted compound representation, fingerprint, and protein representation are connected together to the classifier. The outcome of our model is binary outcome. In addition, we used the CRS model for the drug-drug interactions binary task. As shown in this slide, two CRS models were used to extract the characteristics of a pair of drugs. Then, connect the representations for prediction. In this slide, the network structure of a CRS model is presented. The first layer in the CRS model adapts the convolutional layer. To obtain deeper features, we use the residual network to extract features. At last, the residual network layer is followed by the spatial pyramid network. At this point, we obtain the deep representation of the distance matrix. In the upper right section of the slide, there are two mapping methods of the residual network. The output of the residual network is used as the input of the SPPNet network. In the SPPNet, we set up a three-level pyramid pooling layer. After dimensional reconstruction, we can obtain the compound fixedness representation. In addition, to obtain the protein sequential characteristic, we think of a protein sequential as a sentence with a different number of words. The protein sequential is shown in the bottom figure. We construct the kilogram corpus as the input of the Dot-Vector model. And finally, we can get a fixed length vector as a representative of protein sequentials. Dot-Vector contains two training methods with paragraph vectors the distracted memory model, and the distracted bag of words. We adapt the last one. Next comes the experiments. Our experiments involve CPI experiments and DDI experiments. The datasets we used including Human, C. elegans, and Dude datasets. The data distribution is shown in the table. For the Human and C. elegans datasets, the ratio of the training set, verification, and test set is A to 1 to 1. For Dude dataset, the ratio of the test set to the training set is 13 to 72. We compare the conference of a model with machine learning methods on the test dataset. All the experiments were replicated 3 times, and the average and standard deviation scores are calculated across the 3 runs. In the slide, the results in the table are compared with traditional machine learning methods, and the results in the bar chart are compared with deep learning methods. The general evaluation criteria are adopted to evaluate the experimental results, including area under RLC curve, precise, and recall. As shown in this table, our model is clearly superior to the traditional machine learning methods. In figure, a comparison is made with the latest methods of the deep learning algorithm. Our SPP-CPI model performs better than the latest methods, indicating that the distance matrix can represent the molecular information better than the graph structure. The results of the Human dataset are shown in this table. The comparison results of the Human dataset with traditional machine learning shows obvious advantages in the AUC index, which can evaluate the model comprehensively. Also, we compare with several recent deep learning-based approaches. As shown in the figure, among all the indicators, the performance of our method is optimal. We further compare our SPP-CPI with state-of-the-art CPI approaches on the Dude dataset. The results show that our model performs better on CPI prediction on all metrics. The results were significantly improved at 0.5% RE and 1% RE. Furthermore, we evaluate the influence of using different compound features for CPI prediction on Human and C. elegans datasets. We use the distance matrix feature alone and the fingerprint feature alone to compare with the combination of the two to build CPI models. We adapt the composite AUC matrix as the indicator. The result of prediction model is reported in the table. The combination features appears to be most informative. To find out which network, the compound network or the doctor-vector network, contributes more to the excellent performance of our model, 4 groups of experiments were conducted. As shown in the table, we use the GNN as a comparison. As seen from the AUC index, the characteristic comparison proposed by us achieves the optimal results. Next is the DDI experiment. We use the BioSnap dataset in the DDI experiment. In addition to FE scores and AUC, the PR-AUC metric was used in this experiment. As we can see from the table, our model achieves the best performance. This experiment shows that it is reasonable and appropriate to use the simple distance matrix to represent drugs. It also shows that our model has a strong generalization Finally, we reached the following conclusions. In our study, we have proposed a novel computational framework for CPI prediction, which is an end-to-end deep learning framework. We have used a hybrid network with residual Brooks and primate pooling to extract features from the compound distance matrix. We have used the natural language processing method to process protein sequentials, and experimental evaluations demonstrated that our model can provide more accurate and interpretable CPI predictions than the previous approaches. Our work may provide a promising perspective on the drug design process. That's all. Thanks for listening.